Welcome, ladies and gentlemen. Let's go ahead and take a look at this morning's Bellwork. And so we can graph each of these equations, right, using a different method depending upon what the problem looks like. In the first equation, y equals 1/3 x minus 4, looks like we're all ready to go to graph. It's in slope-intercept form. So go ahead and share with the class when I call on you. What's the y-intercept? The y-intercept of that first line in green. Maddie?
-4.
-4. So we'll go ahead and plot that on the y-axis. And then from that point, we can count out our slope as a fraction rise over run. What's the slope of this one? Carson? 1/3. Thank you. So from this point, we'll go ahead and count out our slope. Looks like up 1/3, get additional point. Up 1/3, get an additional point. We can even count backwards, so long as when you count down and over. Then we'll go ahead and connect those to make a nice linear equation. Oh, we did green, so I'll do green. Raise your hand if you had the first line accurately graphed, the first line in green. Thanks, hands down. Let's take a look at the second one. For this one, right, I could solve for y and graph using the same strategy, plot the y-intercept, and from that point count, right, out my slope number as a fraction rise over run. However, it's quicker and more efficient, given that we're in standard form, to get the x and y intercepts. That was one of the utility. The utility of standard form was to be able to sketch a quick graph. It was easy to find x and y intercepts. And so instead of rearranging that in slope-intercept form like the first equation, I'll leave it as is. And I'll find the x-intercept by plugging in 0 for y, then solving for x, plotting that as a point, and then finding the y-intercept by plugging in 0 for x, solving for y, and plotting that as a point. So here we go. If you were to plug in 0 for y and solve for x, what happens to this y term? Well, when I plug in 0, it disappears, and I'm left with the simple equation 2x equals 9. I can solve that for x by dividing both sides by 2 and get the x-intercept 9/2 or 4.5, 0. We can plot that on the x-axis. Next, we'll go ahead and plug in 0 for x and solve for y. What happens to the x term when we plug in 0? That disappears. I'm left with the simple equation, -3y equals 9. Solving for y by division gives me y equals -3. So it looks like I've got 2 points. I've got 4.5, 0, and 0, -3. I can now connect those, and I'll get the graph using x and y intercepts. Funny feeling. That's a poorly drawn graph, but we'll see. Okay. Raise your hand if you had the blue graph drawn. You have the blue graph drawn? Back to that. Thanks, you guys. All right. So the general form for a linear equation, right, is different depending upon what it is that we're going to do with it. And so slope-intercept form we saw in our Bellwork. What does that look like just with letters? Right? What does that look like just with letters? Holly? Y equals ax plus b, where a would be my slope or rate of change, and b would be my y-intercept, and that's why we call it slope-intercept form. Okay, and so a is our slope or rate of change, b is our y-intercept value. What does standard form look like with letters? So what does standard form look like with letters? David?
C equals ax plus by.
That's absolutely correct. Where we've got the x and the y on the same side, right, equals some number c, and a and b are integers, right? A and b are integers, and we added the requirement that a should be positive too, just for good math manners. Point slope form, that's the one we use to generate a linear equation that satisfied given constraints. That was the easiest way to write an equation. If you know a point on the line and its slope, you can generate its equation using point slope form. Bless you. Raise your hand if you remember that one. What did that one look like with x's and y's and subs? Clara?
Y minus 4y equals
Absolutely. Where a, right, is again my slope or rate of change number, and then x sub 1 comma y sub 1 is any point on the line, or any ordered pairing that satisfies the linear equation. So point slope form is what we use to generate the equation of a line that satisfies some particular condition. Awesome. All right, we're going to be using both of those, all three of those, I should say, throughout this unit as we work with systems. I'm going to go ahead and pause the recording as we take it. Oh, no, I already came around, so we're good to go. We'll keep the party moving. So today we're going to be working with systems for the first time, and we're going to solve them several different ways. We're going to solve systems using tables, graphs, and then the substitution method. You'll also need your grapher because we're going to be using some of the built-in programming on your TI grapher, and so we will need a graphing calculator later in today's class period. All right, so let's go ahead and get started. A system of equations is just two or more equations joined by the word and or brackets. Okay, and so instead of just having a single equation and finding the solution to a single equation, like we've done, a system of equation combines two or more equations into a single problem. A solution to a system is a point x comma y that satisfies all of the equations in the system. Notice how the solution to a system, right, is an ordered pair, x comma y, versus the solution to an equation like we saw back in Unit 1 is typically just x equals 3, right, or y equals -7. Well, when we're dealing with a system of equations, then typically our solutions are a point, an ordered pair, x comma y, right, and it's got to satisfy each of the equations in the system. Constraints is just a synonym for the equations in the system. So another name for the equations that make up a system is constraints. And this comes from the real-world applications of systems. And so we think of being able to find the optimal solution when working within the given constraints, right? What's the minimum distance and gas, right, that we have to buy to complete all our deliveries on our delivery route? Well, we have certain constraints, like speed limits, stoplights, traffic, stuff like that. And so all those would be constraints. What's the minimum amount of packaging, right, that you can use for our shipping business? Well, we've got things like the size of the package and the product that's going to fit inside. What's the most efficient way to pack that, and so on and so forth. So constraints are another name for the equations in the system. All right, so what's a system of equations? Well, that's the two or more equations joined by the word and or brackets. In this case, right, the system of equations would be y equals 1/2 x minus 4 and 27x plus 9y equals 27. Well, if that's the system, what's the solution to the system? Well, the solution to that system is a point x comma y that satisfies all of the equations in the system. Well, is there a point that satisfies all of the equations in this system? Well, if the red line is the collection of all points x comma y that satisfy the first red equation, and the green line is the collection of all ordered pairs x comma y that satisfies the second equation, is there a point that satisfies both equations? Zoe? What do you think it is? Close. I'm thinking 1, 2, 2. It looks to me like 2 comma, is that -3 or -4? -3, -4? Well, let's check. If I were to plug in, right, my point x comma y to be a solution to the system, it has to satisfy each equation. So let's try 2 comma -4 in the first one. If I were to plug in 2 for x, I would get half of 2 is 1. 1 minus 4 is -3, right? Is -3. And so it's not 2 comma -4. It looks like 2 comma -3. Let me see if that works though. So 2 comma -3 satisfies the first one, but I'm not sure about the second one. Let's plug in -3 rather. And let's see if it satisfies the second equation. Here we go. 27 times 2 is 54. Plus 9 times negative 3 is negative 27. Does 54 minus 27 equal question mark 27? Taylor?
Yes.
Yes, it does. And so we've got a solution because half of 2 is 1 minus 4 is negative 3. Satisfies the first. And 54 minus 27, it satisfies the second. If my point x comma y satisfies each of the equations in the system, then it's a solution. Visually, I can see that on a graph, right? It's the point that lies on all of the curves at the same time. So what's the system of equations? What's the solution? It looked like 2 comma negative 3. Now let's take a look at another system. So suppose now we're dealing with some different kinds of equations, like y equals x squared. We know back from unit 1, this is our parent function, right? Our parent parabola, total bowl shape, right? Whose vertex is 0, 0, and whose orientation is right side up. And so from the vertex 0, 0, we can get a quick sketch of that by going out 1, up or down 1. In this case, positive x squared, I'm going to go out 1, up 1 squared. Carefully plot those points. Out 2, up 2 squared, and that's 4. So back to your vertex. Out horizontally 2, and up 2 squared is 4. And then, so negative 2 comma 4 would also be there. Out 3, up 3 squared is 9. Out 3, up 3 squared is 9. And so it looks like we've got a nice parabola. Remember, no corners or kinks like absolute value. This should be a nice smooth bowl shape. So let's go ahead and do that. Great. Now let's take a look at the second equation in my system. Y minus 1 equals negative quantity x minus 1. What? How in the world are we going to graph that? Well, I could certainly rearrange that, right? However I want. I could make it look like y equals mx plus b, or y equals ax plus b from our slope-intercept form. And yet, it's actually easiest to leave this unchanged as well. This is currently in one of our 3 forms. Quietly tell your partner which form the green equation is currently in from our linear equations recaps. So which form is that currently in? Okay, go ahead and share with the class. Sammy and Carson?
Point slope form.
Point slope form. Thank you, point slope form. In fact, it's easy to graph this. Unchanged, I'll simply plot the point that's on this line and then count out its slope number as a fraction rise over run. Remember, my point slope form has a negative, has the subtraction built into it. And so this is y minus y sub 1 is equal to, looks like negative 1 times x minus x sub 1. And so actually, the point on this line is positive 1, comma positive 1. And the slope, m, is actually negative 1 over 1. And so I could plot this graph without rearranging that second equation simply by plotting the point 1 comma 1 and counting out my slope number as a fraction rise over run, down 1 over 1, down 1 over 1, down 1 over 1, and so on. I can even count backwards if I'm careful. It's pretty sweet. Mr. Frisk, that's a good graph. Thank you. I should stand on that side of the board more often. Hey, I'm going to say that. All right. Does it appear as though there's a point x comma y that satisfies each of the equations in the system? Yeah, right? What's one solution to this system? Go ahead and tell your partner and be ready to share with the whole class when I call on you. So what's one solution to the system? Matt and Hope.
1, 1.
1, 1. Let's check it out. So we think 1, 1 is a potential solution. Let's see. Does 1 squared equal 1? Yes, it does. 1 minus 1 is 0. Does 0 equal the opposite of 1 minus 1 is also 0? Yes, it does. And so 1 comma 1 is a solution. What's the other solution for this one? Andrew and Grace?
Negative 2, 4.
Negative 2, 4? I don't know. Let's check. So negative 2 comma 4. In order to be a solution, it has to satisfy each of the equations in the system. Let's check. Does 4 equal question mark negative 2 quantity squared? Yes. So it satisfies the first. Does 4 minus 1 equal question mark the opposite of negative 2 minus 1 is the opposite of negative 3? What? Does 3 equal the opposite of negative 3? Yes, it does. Winner, winner, chicken dinner. This particular system has 2 solutions. And so sometimes there's more than one point x comma y that satisfies all the equations in the system. In that case, there's multiple solutions. Great. Leave that blank for a minute. Let's go ahead and take a look at one more. Y equals opposite of x squared. Hey, we just graphed the parent function y equals positive x squared, right? How is this one going to look different? Chloe? Good, it'll open upside down. Same steepness, right? Same steepness, but opposite orientation. So everybody, let's carefully get those points. 0, 0, and then out 1, down 1 on either side of the vertex. Out 2, down 4 on either side of the vertex. Out 3, down 9. Go ahead and carefully plot that in a nice smooth bowl shape. And y minus 1 equals negative quantity x minus. This looks like the same. Doesn't this look like the same line? It looks like it has the point positive 1 comma positive 1 and a slope of negative 1 over 1. And so when I photograph this, from that point I can count down 1 over 1, down 1 over 1, down 1 over 1, careful, and backwards. Go ahead and tell your partner the solution to this system. Be ready to share with the class when I call on you. What's the solution to this system? Jimmy?
No solution.
No solution. Raise your hand if you had no solution for this one. Yeah, if there's no point that lies on both curves simultaneously, there's no intersection, then there's no point x comma y that satisfies each of the equations at the same time. This particular system has no solutions. Good job. Thank you. So we still write that. No solutions. Cool. 2 more vocabulary words. A consistent system is what we call a system that has 1 or more solutions. And so if there is a solution to the system, 1 or more solutions, then it's called a consistent system. If there's no real solutions, then it's inconsistent. Okay, and so if there's no solutions, then it's inconsistent. Now we can go back and label each of those systems, right, in that blank underneath the graph. Let's label those previous 2 systems consistent or inconsistent. All right, so 1 or more solutions, that's consistent. Right? If there's 1 solution, it's consistent. If there's 2 solutions, it's consistent. If there's infinitely many solutions, it's consistent. So as long as there's a solution, 1 or more, then it's called a consistent system. Versus no solutions, that's inconsistent. So we can label those systems accordingly. All right. Now that we know what a system is, we're going to go ahead and look at some additional methods to use for solving. So we've already seen how graphically the solution to the system was a point or points of intersection. Now we're going to solve using tables. Well, we'll need our graphing calculator for this, and so please make sure you have yours at the ready. Graphically, the solution to a system is the point of intersection, or the solutions are points of intersection. Let's take a look at y equals 45 minus 5x and y equals 5 plus 3x. We're going to solve this example using tables first. And so let's go ahead and in our y equals menu, enter our original functions in y sub 1 and y sub 2 respectively. So we'll go ahead and clear out any other graphs that we might have. We're going to go ahead and enter our first equation, 45 minus 5x equals y1. Let's do for that one. So 45 minus 5x, and our y sub 2 will enter 5 plus 3x. So first we'll enter our function definitions in our y equals menu. To solve this using a table, I'm going to go ahead and change mine back to auto. So I'm going to go second table set. And for my table set, I'm going to start at, looks like -2. I'm going to have my delta table or change in table value, my step size set at 1. And I'm going to set my independent to automatic. And so I'll have automatic for my independent and dependent. That way it'll automatically construct the table going by integer, right? Integer values, and I'm going to be able to scroll back and forth. And so you can set your table however you like. I'm going to go ahead and take a look at this and see. There we go. And so as I look at this table, right, I'm trying to see if there's a point that satisfies each of the equations in the system. In terms of a table, I'm looking for a point that has the same output y coordinates paired with a single input value. So let's scan. Can we find a single x value that's paired with the same y value in each equation? Well, I'm getting farther and farther away, so that's not doing very good. Let's see. That's not doing very well. Oh! I found a winner. Did you guys find a winner? Yeah. Find one. So what's our winner here, Nicole? 5, 20, a single, right? A single output y value paired with the same input x coordinate. So it looks like, oh, and flip that back. There we go. So we're looking for a single x value that produces the same output y value in each equation, or all equations, I should say. However, we still write our point as a solution x comma y, ordered pair. And so my answer would not be 5, 20, 20. It would not be 20, 20, right? What would my ordered pair solution be? Carson? 5, 20. Good. That input 5 just produces the same output 20 in each of my equations. It's still a single point, 5, 20. However, we have to be careful. We want to make sure that there's no other, right, solution points in my table. So as I continue scrolling down, does it appear as though there's going to be another solution if I continue scrolling? Right? Does it look like there's going to be another solution if I continue scrolling? Holly? No, how come?
Because the y100 equals 0.
Yeah, it looks like my y1 is getting more and more negative, and look at my y2 values. Getting more and more positive, right? Now that doesn't mean that there's not going to be another solution there in general if we don't know our equations for y1 or y2. But in this case, we do know our equations. What type of graph is produced by that first equation, right? What type of graph? 45 minus 5x equals y1. Ryan?
A line.
A line, right? In fact, it would be a negatively sloped line. What kind of graph is produced by the second equation? Right, that second equation, what kind of graph does that make? Matt?
Be like
Y equals 5 plus 3x.
wouldn't it just be like not a straight line, but like I don't know.
Well, if I look at my equation, it looks kind of like the Bellwork question, right? Kind of like the first equation, but instead of being y equals 1/2 x minus 4, it's y equals 5 plus 3x. If I reordered that, and rewrote it as y equals 3x plus 5, then I recognize it as slope-intercept form of a linear equation. What type of graph does a linear equation make? Matt? I'll give you a hint. What type of graph does a linear equation make? Yeah! And so if I graph that second equation, y2, 5 plus 3x, I'm going to have a positively sloped line, right? So I've got a negatively sloped line. I've got a positively sloped line. Are the slopes the same? No. How many points of intersection are they going to have at most? Clara? Yeah, one and only 1 point of intersection. There's no way that that's going to curve back around. So I agree. There's one solution, and we found it. We're done. Great. Let's take a look at another. Thank you, you guys. So try solving this system using your calculator's table feature. xy equals 30, and x minus y equals 1. How should these equations look before I can put them in my grapher? So how should these equations need to look before I can put them in my grapher? Logan? How do these need to look before I can enter them in my grapher? Well, can I enter this in my grapher right now? No? How come? Well, if I go to enter this in my grapher has y equals, right? And right now, my equations have x and y on the same side. And so I'm not able to enter those as they're written unless I do a little bit of groundwork first. I need to solve those for y so that I can enter them in my y equals menu. You guys see? So let's go ahead and solve those for y. The first one looks like division. Division will get my y alone. If I solve for y, I could divide both sides by x. That would give me 30 over x. And then x minus y equals 1. I could solve that by adding over the y and subtracting over the 1. Or subtracting over x and dividing both sides by -1. The choice is yours. I'm going to go ahead and add over the y, subtract over the 1, and I get y equals positive x minus 1. You can verify that you get the same thing. After rearranging to solve for y, we're ready to go with our y equals menu. Now you see we can enter them. My first one, 30 over x, I'll put equal to y1. My second one, y equals x minus 1, I'll put as y2. Everybody make sure you have yours entered correctly. Is good? All right, we're checking this out on the table now. So once again, back to second graph, going to the table feature, and I'm scanning. And I'm scanning. And I've got my y's getting smaller in the blue y1 and bigger in the red y2, so I'm going to go back the other way. I'm not seeing any x value that produces the same output in each equation. But I'm on the right track here. Let's see. Oh! Winner, winner, chicken dinner. Did you guys see it? I found one. All right, what's one solution? What's one solution to my system of equations? Evan?
6, 5.
6, 5. Excellent. 6, 5 is one solution to my system, and I would still write that as an ordered pair, 6, 5. As I check algebraically, I see that 5 does equal 30 divided by 6, and I see that 5 does equal 6 minus 1. Hooray! So I'm feeling pretty good about that. Awesome. What questions do you guys have about our solving with the table? Well, I've got one. What happens if we zoom 6 in a standard viewing window? Everybody press zoom 6 to look to your default -10 to 10. I see my 6, 5 solution that Evan told us about right here. There's my 6, 5. But what did I miss by using the scroll on the table? Right, what did I miss? Sammy?
That there's the two whatever.
Yeah, it looks like there's this other branch over here on that first blue function, y equals 30 over x, which we'll call a hyperbola. There's another branch over here, and I missed an intersection point completely. That's why a table, right? A table is limiting, I believe, in our ability to solve. What if we had a non-integer value, right? If it was a fractional point of intersection or something like that, we can miss it if our table is set to integer values. Or if we have more than one solution and we're scrolling, we have to keep scrolling up or keep scrolling down. And for that reason, I think that using the table feature, right, can be limiting. Graphically, we can see there's two solutions and we missed one entirely. No problem, we can still find it. Now that we know another one's over there, right, we can scroll up and locate that. And the table feature, it looks like negative. Hey, there it is. So it looks like easy there. Easy, easy. Got all carried away. Lag. There it is again. So it looks like -5, -6. Is that right? -5, -6? I'm going to check that algebraically too. So we found another one, -5, comma, -6. Does -6 equal 30 divided by -5? Yes. Does -6 equal -5 minus 1? Yes, it does. And so we found two solutions. We better write them down. So we've got 6, comma, 5 was one of them, but -5, comma, -6 was another one. We want to make sure that, right, we're being aware that there might be more than one solution to a system, or none at all. Great. So we've got those. Now let's go ahead and solve graphically. So let's go ahead and take a look at our original here. And now these are easy to sketch a quick graph using slope-intercept form because they're already arranged y equals ax plus b. Go ahead and share with the class the y-intercept of the first one, and I'll do green. So what's the first equation, the y-intercept? Alex?
-1.
-1, thank you. We can plot that. What's my slope as a fraction, rise over run? Kai? Good, so we'll go up 5, 1, 2, 3, 4, 5, and over 1. Up 5 and over 1, I'm off the graph. I can go down 5 and over 1. And now I'll carefully sketch that in green. Next, we'll graph the second line. What's the y-intercept of the second line? What's the y-intercept of the second line? Luke? 3, thank you. So we'll plot that. And what's my slope as a fraction, rise over run? Kylie?
-2.
-2 over 1, thank you. -2 over 1. Everybody carefully get that second line. Landing it in red. Okay, what's the solution to this linear system? What's the solution to this linear system? Grace? 1/2, 2. Maybe. 1/2, comma 2. What's different about this graph that makes it harder to see my solution? What's different about this graph that makes it harder to see my solution? Zoe? Yeah, it's not on a lattice point, an integer point, x comma y, right, with integer coordinates. And so clearly, right, my graphing method has its limitations when we're dealing with a fractional point of intersection or an irrational point of intersection, right? We can't find that visually just by looking. Only in special circumstances where my point x comma y has integer coordinates is it easy to see. And then only if I have a grid, right? if I just had my own paper that I was making, then it'd still be hard to see. And so tables have their limitations, graphing has their limitations, particularly if it looks like a fractional point of intersection. That's okay though. We can use our graphing calculator to find that numerically and get an approximation. So everybody find your steps. Everybody find your steps. This is powerful. So we're going to solve graphically using our calculator to get a decimal approximation. In order to do that, we'll enter our equation into the y equals menu just like before. In order to do that, they must be solved for y. It looks to me like we are solved for y. And so we're going to enter our original equations in the y equals menu. That's step one. Everybody at this time, please do so on your grapher. So y1, I'll do 5x minus 1. y2, I'll do negative 2x plus 3. After we enter those in our grapher, right, then we're going to inspect the graph and look for intersections. And so everybody, let's inspect the graph and look for intersections. And it looks like there is a point of intersection there, right? And so I know there's going to be at least one solution to this system. I just don't know what it is yet. So now we'll do second trace for the calculate menu. Everybody find it. So we're going to do second trace. Second trace on the calculate menu, and I want to select the fifth option, intersect. And so we'll go ahead and do second trace intersect. After selecting the fifth option, the calculator asks me, right, for the first curve. Is this blue equation my first curve? Yes, it is. So I'll press enter to tell the calculator, yes, that's what I want you to use for the first curve in my system. Second curve is the next prompt. Yes, it jumped to the red one. I want you to use that red equation for my second curve in the system. And then a guess. I'm going to use my arrow keys to scroll along, right, till I get close to my point of intersection. If there's just a single one, then it doesn't matter. But if there's multiple points of intersection, the calculator is built to jump to the nearest point of intersection. And so sometimes you have to manually adjust, right, the cursor using the left or right arrow keys till you get close. So my guess, I'll press, and for a third and final time, your calculator, right, isn't done. It hasn't calculated the intersection until it says intersection on the bottom. Otherwise, you're just using the trace. And so unless it says the word intersection, then you haven't used the built-in software. Everybody, make sure that you produce the word intersection, and when you have the word intersection on the bottom, then I want you to show your partner. If they're having trouble getting intersection, then help them with the steps. So second, trace, calculate. First curve, enter. Second curve, enter. Guess, enter. Ugh, was it 1/2 2? Would we have gotten this by guessing? No, we would not have gotten that by guessing. Look at that. 0.57142857. 1.8571429, and yet there's a real solution and we can see it visually, right? And so table has its limitations because you don't know if there's more just by looking and scrolling on your table, and it takes a long time. Graphing has its limitations by hand, right? Because what if you have a fractional point of intersection, and then now when we use the built-in capabilities of the grapher, that's just an approximation as a decimal, right? That's not the exact value. However, we could follow up here. If we were to write down these decimal places, I wonder if there's a rational solution to this. It looks like there would be. Let's go ahead and write down those decimal places. 0.57142857. That looks like it's going to repeat, doesn't it? And what about 1.8571429? I wonder if that is rational. Let's see. I'm going to go ahead and enter 0.57142857, and I'm going to do math frac to change this into a fraction if it will. So I'm going to do math frac, and I'm going to see if it changes that into a fraction, and enter. No, it didn't. Make sure. 57. If this pattern continued, what would it be? 57142857. What would come next? 1, 4. 2, 8. 5, 7. What will come next? 1, 4. Let's try. I just changed the Oh! My golly. I knew it was going to work out because we had two linear equations here nicely. 4 sevenths. 4 sevenths. I wanted to guess 4 sevenths. I want to guess 1/2. Right along with Grace. Right? And so clearly we've got our limitations. I bet we could change the other one into 1.8574729. But let's figure out an easier way. We'll do that now with an algebraic means. And so we've got limitations whenever we're using tables, whenever we're using graphs, even with the graphing calculator, right? We've got limitations. Now we'll go ahead and use our algebraic powers, right, in order to find that solution exactly and algebraically without having to worry about tables or graphs or decimals. So tables and graphs may not always give exact solutions to a system. We're going to look at methods of finding exact solutions with algebraic manipulation, and this is the power of algebra. So let's go ahead and take a look at one of these pencil and paper methods, and that's called the substitution method. Solving the following system using substitution is easy. Look at that first equation. It's already solved for y. So we know that y is the same as 2x plus 3. In the substitution method, don't do anything yet. We're going to go ahead and do it together. I just want to show you kind of the scheme here. So in the substitution method, we're going to substitute what y equals, in this case 2x plus 3. We're going to replace the y in the other equation with its equivalent statement, 2x plus 3. Now we've got a single equation with a single variable, and we'll be able to solve that for x, and then go back to the original to figure out what y is. So the general scheme is we want one of the equations solved for one of the variables. We'll replace that variable in the other equation with what expression it's equal to, and we'll solve that single equation, single variable, and then go back to the original. So let's go ahead and see. Let's do this one together. In the first equation, y is already solved for. It doesn't matter. It could be x is already solved for. But we need one of the equations to be solved for one of the variables. Check. It looks like y is solved for in the first equation. What is y equal to? Y is equal to 2x plus 3. And so we're going to rewrite the second equation. Except everywhere I see a y, we're not going to put y. We're going to put 2x plus 3. Everybody, let's do that. 3x minus 4 times y. Except everywhere I see a y, I'm going to put what it's equal to. It's equal to 2x plus 3. Now look, we have a single equation with a single variable. We can now solve for x, and then go back to my original equation where I put the asterisk to figure out what y is, and write my answer as a point x comma y. So let's go ahead and do that. I get 3x distributing through, negative all the way through. Watch you guys. Negative 4 times positive 2x is negative 8x. Negative 4 times positive 3 is negative 12. Watch your signs. Combining like terms, same side, same operation gets me negative 5x. Minus 12 is equal to negative 42. Opposite side, opposite operation. Adding 12 to both sides gets negative 5x equals negative 30. And now we can finish it out by division. Dividing both sides by negative 5 isolates x. And it looks like x equals negative or negative is positive, and 6. I'm getting 6. You guys getting 6? Is x equals 6 the solution to the system of linear equations? No, I know the solution to a system is a point, x comma y. And so where do I go to find the y value that corresponds to this x value? We can go right to that original equation. That's why I put an asterisk there to remind me. That's where I can go to figure out y. Once I know x, I know that y equals 2x plus 3. We just found x to be 6. Therefore, y must equal 2 times 6 is 12 plus 3. y must equal 15. So my potential solution is 6, 15. But I'm not going to box that, right? What should I do before I box that point? Ryan?
Check.
Yeah, I can check that by plugging it into each of the originals. Let's do that now together. So, does 15 equal question mark 12 plus 3? Yes, it satisfies the first. Does 3 times 6, that's 18. Does 18 minus 60 equal negative 42? Oh, I'm going to write that one down. 18 minus 60 equal negative 42. 42, 24. Yes, it does. And so I know now that 6, 15 satisfies each of the equations in my system. Therefore, it's a solution to the system of equations. So that's the general scheme. For substitution method, I make sure that one of the equations is solved for one of the variables. Sometimes I have to do that. Sometimes it's all ready to go. Doesn't matter if it's x equals or y equals, but I need to have one of the equations solved for one of the variables. Then I'll rewrite the other equation, but substitute in what that variable is equivalent to generate a single equation with a single variable, solve, and then go back to the first equation to get the corresponding value. All right, let's try it out again then. So I am still looking for that 4/7. Our calculator couldn't tell it to us, but we can get it with ease algebraically. Is one of the equations in the system solved for one of the variables? Yeah, both of them, right? The first one solved for y, the second one solved for y, and so I can choose either one to be my substitution expression. I'm going to go ahead and let that first equation, which is solved for y, I'm going to take 5x minus 1, and I'm going to substitute it into my second equation everywhere I see a y. So I'm going to rewrite the second equation, but instead of putting y, I'm going to put 5x minus 1. I'm substituting in what y equals. That equals negative 2x plus 3, and now you see I have a single equation with a single variable we can solve. I'll add 2x to both sides. 7x minus 1 equals 3. Adding 1 to both sides gets me 7x equals, oh, Grace, I'm seeing it. When I divide both sides by 7, there's that elusive x value that we couldn't quite pin down. It looks like x does equal the 4/7, right? The 4/7 that I was hoping to find when I math fracked it and I wouldn't change it into it without some doctoring. But we never did find the y coordinate exactly, did we? We just had, right, that 1.857 business. So let's go ahead and see where we can go to y. Well, the first one was already solved for y. The second one solved for y. We can go to either one. I'll go to that first one. Y equals 5 times x minus 1. We just found x was the red 4/7. So y must equal 5 times 4/7 is 27 minus 1. And let's see if we can't figure out what that is as a fraction. So to combine terms through addition or subtraction, where one of them is a fraction, we need a common denominator. Looks like 7ths is the winner. So by changing the second term to 7/7, I get 27ths minus 7/7 equals 13/7. All right. Let's go ahead and see if that 13/7. Let's see if that was my decimal that we got from second calc intersect that we never knew. So let's go back. We had right here 1.8571429. We think it's 13/7. Let's check. Ready? 13/7. Survey says 1.857142857. Right? And we got it algebraically, and we got it exactly, and we did a better job than the calculator did. It could only give us that decimal approximation. So that's pretty sweet. Awesome. What kinds of questions do you have about the substitution method thus far? Okay. Then let's go ahead and take a look at another. In this system, is one of the equations currently solved for one of the variables? Victoria? No. But can we get it there? Yeah, we've got our choice here. We could solve the first one for y or the second one for x. Does it matter? No. We've already done a couple with y solved for, so I'm going to go ahead and solve the second one for x. In order to do that, I'll go ahead and rearrange through subtraction, and I'll get x equals negative 2y plus 2. This will become my asterisk equation. This expression is what I'm going to substitute into the first equation everywhere I see an x. So let's do that together. I'm going to rewrite the first equation, 3x plus y equals 16. Except everywhere I see an x, I'm not going to put x, right? What am I going to put? Dylan? What does x equal?
Oh, x equals negative 2y plus 2.
Absolutely right. I'm going to replace my x with the negative 2y plus 2. And now I've got, check it, a single equation, single variable now we can solve. Watch your signs, you guys. Let's distribute. I get 3 times negative 2 equals negative 6y. Plus 3 times 2 is plus 6. Plus I still have the y chilling outside equals 16. Combine like terms. Same side, same operation. So we'll go ahead and combine like terms. I get negative 5y plus 6 equals 16. Opposite side, opposite operation. We'll subtract 6 from both sides to isolate the y term. And I get negative 5y equals 10. Dividing both sides by negative 5, I get y equals negative 2. But that's not all. That's only half the system solution. But I've got my x equals asterisk equation here, where I can go back in and rewrite to figure out the x value. X must be given by opposite of 2 times y plus 2. We just decided y was negative 2. I don't know what happened there. I still don't know what happened there. Okay, round 3, negative 2 times negative 2 plus 2. And we'll finish it out. Watch your signs. I get opposite. Negative 2 times negative 2 is positive 4 plus 2. 4 plus 2 is 6. I'm getting 6. And I don't know what's going on with that. But I'm going to do my ordered pair x comma y and check it. And so I'm getting negative 2 comma 6, and we're going to check it. Does 3 times negative 2, that's negative 6. Nope, we need to switch these, right? So 6 times negative 2, is that better? Let's check. Does 3 times 6, 18, plus a negative 2 equal question mark 16? Yes. So the first is satisfied. Does 6 minus 4 equal 2? Yes. So the second one is satisfied. So we found our winning combination. That's great. Okay. Let's go ahead and summarize for the day then. A written response from each of you, and then I'm going to call on you to share with the whole class. I'll pause the recording and give you a minute to write those down. Okay, so what does the solution set to a system look like in a table? So what does it look like when you're in a table? Taylor?
Like x equals the value, and then y1 and y2 are the same.
Absolutely. The same y value produced for a single x input. So same y value produced for a single x value. Thank you. What does the solution set to a system look like graphically? So what does it look like when you're looking at the graph? Matt?
It's like the intersection.
Absolutely. An intersection point or points. Good. Thank you. How many solutions does an inconsistent system have? So inconsistent has how many solutions? Andrew? 0 solutions. Good. Raise your hand if you have the same as Andrew. 0 solutions to an inconsistent. Good. How many solutions does a consistent system have? Nicole?
One more.
Good. 1 or more. It could be 1, it could be 2, it could be infinitely many, but 1 or more. So it just requires that there are solutions to be consistent. And what has to be true before you can substitute? And so what has to be true before you can substitute in our substitution method? David?
Let's find that actual one first.
Yeah, we need one of the equations solved for one of the variables. And so one equation must be solved for one of the variables. So I'll say that one of the equations must have x equals, right, isolated, or y equals by itself in order for you to use the substitution method. Nice job, you guys. What questions do you have about our closer today? Okay, and the rest of the time you're to get started on assignment number 1. I'm going to go ahead and save the recording and upload it to our Moodle site.